Hello students, welcome to EPG Pathshala. I am Sumalay Roy from Department of Physics and Astrophysics of University of Delhi. Today we are going to talk on module Properties of Clebsch-Gordon Coefficients under the paper Quantum Mechanics. So students, let us see what we are going to learn in this module. We will be knowing how to derive the orthonormal properties of the CG coefficients. We'll learn some useful symmetry relations between the CG coefficients. We'll learn how, with the help of the recurrence relations, one can derive the expression for the CG coefficients. We'll know a few examples to evaluate the CG coefficients. Orthogonality relations. Orthogonality relations, let us rewrite equation 20.9 in the form a kth vector Jm, which is equal to a sum over m1 and m2, which is a product of two vectors, scalar product j1, j2, m1, m2 with jm, and the kth vector j1, m1, j2, m minus m1, which is equal to sum over m1 into sum over m1, sum over scalar product of the two vectors j1, j2, m1, m minus m1 with jm, and the kth vector j1, m1 with j2, m minus m1, where from now onwards we denote the Clebsch-Gordon coefficients C subscript m1, m2, m and superscript j1, j2, j as the product of these two vectors j1, j2, m1, m2 and j. Further, in writing the latter part of the right hand side, we observe that since m1 and m2 are not independent but are given by the relations m equals to m1 plus m2, we use it to take care of the summation over m2 and writing for m2 is equal to m minus m1 wherever it appears. As stated in the preceding module, the CG coefficients are elements of orthonormal properties of CG coefficients. Unitary transformation and therefore must satisfy the orthonormal properties. These can be shown in a straightforward way using the fact that the eigenstates are orthonormal, that is, vector Jm multiplied by vector J prime m prime equal to delta Jj prime delta mm prime, with the standard phase convention chosen such that the CG coefficients are real. We substitute equation 21.1 in equation 21.2 to have Jm dot J prime m prime equals to delta Jj prime delta mm prime, which is again equal to sum over m1 and m1 prime dot product of two vectors j1, j2, m1, m minus m1 to jm, with multiplied by the dot product of two vectors j1, j2, m1 prime m prime minus m1 prime with j prime m prime into the dot product of the vector j1, m1 and j1, m1 prime into j2m minus m1 product with j2m prime minus m1m prime. Using the fact that the eigenstates are orthonormal, which means the dot products of j1m1 with j1m1 prime multiplied by j2m minus m1 with the dot product with j2m prime minus m1 prime is equal to delta m1 m1 prime into delta mm prime. Equation 21.3 reduces to sum over m1 and the vector multiplication of j1, j2, m1, m minus m1 into jm and the dot product of j1, j2, m1, m minus m1 with j prime m, which is equal to delta jj prime. With this orthogonality relation, one can obtain the inverse expansion of 21.1, which is j1 vector j1 m1 multiplied by vector j2 m minus m1 which is equal to sum over j and multiplied by vectors j1, j2, m1, m minus m1 dot product with jm into a great vector jm. Thus, multiplying both sides of this equation by j1, j2, m1, m minus m1 with the dot product with j prime m and summing over m1, we get sum over j, get vector jm, sum over m1, j1, j2, m1, m minus m1, j prime m multiplied by j1, j2, m1, m minus m1, jm, which is equal to m1 into j1, j2, m1, m minus m1, j prime m into ket vector j1, m1, j2, m minus m1. The quantity in the parenthesis on the left hand side is just delta jj prime according to equation 21.5. Thus we have sum over j, jm delta jj prime, which is equal to sum over m1 with a vector multiplication of j1, j2, m1, m minus m1 multiplied with j prime m with a vector j1, m1, j2, m minus m1. Symmetry relations of Clebsch-Gordon coefficients. Now our j prime m ket vector equal to sum over m1 multiplied by sum over m1 into j1, j2, m1, m minus m1 multiplied by j prime m vector into the ket vector j1, m1 operating over j2, m minus m1, which is the same as equation 21.1. Using equation 21.6, another orthogonality condition which can be seen as an expression on the orthonormality condition on the rows and columns of a unitary matrix can also be deduced. We here write this equation without deriving it, that is sum over j1, j2, m1, m minus m1, the dot product of jm vector into j1, j2, m1 prime, comma m prime minus m1 prime, jm prime, which is equal to delta m1, m1 prime, delta mm prime. Symmetry relations of Clebsch-Gordon coefficients. Among the three number pairs j1, m1, j2, m2 and jm equals to m1 plus m2, we have observed certain symmetry as a result of the triangular relation between j1, j2 and j and the m-sum rule. We mention some simple relations which exist between C coefficients when the roles of the angular momenta are interchanged. These relations may prove useful in evaluating the C coefficient from those already determined. Now j1, j2, m1, m2 with a product of jm vector equals to minus 1 to the power j1 plus j2 minus j to the vector product j2, j1, m2, m1 with jm, which is equal to minus 1 to the power j1 plus j2 minus j with a vector product j1, j2, minus m1, minus m2 with j, minus m, which is again equal to j2, j1 minus m2 minus m1 with a product with a j minus m equal to minus 1 to the power j1 minus m1 into 2j plus 1 by 2j2 plus 1 to the power half into the vector product of j1 m1 minus m and j2 minus m2 into 2 to the power minus 1 to the power j2 plus m2 into 2j plus 1 by 2j1 plus 1 to the power half into the scalar product j2 minus m m2 with j1 minus m1. Determination of the Clebsch-Gordon coefficients. Note that the 3j symbol introduced by Wagner and used often in many textbooks is related to the notation used here as the matrix j1, j2, j3, m1, m2, m3 equal to 1 by square root of 2j3 plus 1 into minus 1 to the power j1 minus j2 minus m3 with the scalar product of the two vectors j1, j2, m1, m2 and j3 minus m3. Determination of the Clebsch-Gordon coefficients. Let us outline briefly the procedure for evaluating the CG coefficients. The simplified derivation is based on a recurrence formula for the coefficients. The first step is to apply to both sides of equation 21.1 using on the right hand side recurrence relation for the Clebsch-Gordon coefficients, which is j square equal to j1 square plus j2 square plus 2j1 dot j2, which is again equal to j1 square plus j2 square plus j1 plus into j2 minus plus j1 minus into j2 plus 2j1z into j2z. We recall from the study of previous modules that while state vectors are the eigenvectors of j square and jz, the states j1 m1 and j1 m2 or m1 m minus m1 are respectively the eigenstates of j1 square, j1z and j2 square, j2z. We use the relations given in equation 20.2 and 20.3 and 20.7, and for the raising and lowering operators, employ the relations equation 18.23 and 18.24. We finally get, after some manipulations, for details see Elementary Theory of Angular Momentum by M.E. Rose. We see after some manipulations the recurrence relation for the Clebsch-Gordon coefficients given by recurrence relation for the CG coefficients. J into j plus 1 minus j1 into j1 plus 1 minus j2 into j2 plus 1 minus 2m1 into m minus m1 with a scalar product of the two vectors j1 j2 m1 comma m minus m1 and jm equals to, within the third bracket, j1 minus m1 plus 1 into j1 plus m1 into j2 plus m minus m1 plus 1 into j2 minus m plus m1 to the power 1 by 2 multiplied by the scalar product of the two vectors j1 j2 m1 minus 1 comma m minus m1 plus 1 with a scalar product jm plus within bracket j1 plus m1 plus 1 into j1 minus m1 into j2 minus m plus m1 plus 1 into j2 plus m minus m1 to the power half multiplied by the scalar product of two vectors j1 j2 m1 plus 1 comma m minus m1 minus 1 and jm. This is the recurrence relation for the Clebsch-Gordon coefficients for fixed values of j1 j2 j and m in the projection quantum numbers. Note that while the CG coefficients on the left hand side has in its argument the quantum number m1, the first term on the right hand side has m1 minus 1 and the second term has m1 plus 1. Evaluating the CG coefficients for the case j2 equals to see how this recurrence relation is employed to get the expression of the CG coefficients, let us consider the specific case when j1 is coupled to j2 equals to 1 to get the value of the total angular momentum j equals to j1 plus 1. Let us, for brevity, call the vector j1 1 m minus mu plus mu and j1 l plus l comma m vector is equal to x mu, where mu is m minus m1 is actually m2, which can take the values minus 1, 0 and plus 1 for j2 is equal to 1. Using equation 21.9 and substituting the values j2 equals to 1, j equals to j1 plus 1. We get three recurrence relations for mu equals to 1, 0, minus 1. Mu equals to 1 is to 2 into j1 minus m plus 1 into x1 equals to 2 into j1 plus m into j1 minus m plus 1 to the power half x0. Mu equals to 0. In this case, 2j1 x0 equals to 2j1 minus m plus 1 into j1 plus m to the power half x1 into x1 plus 2 into j1 plus m plus 1 into j1 minus m to the power half to x minus 1. In case of mu minus 1, 2 into j1 plus m plus 1 into x minus 1 equals to 2 into j1 minus m into j1 plus m plus 1 to the power 1 by 2 into x0. From these relations, we can determine only the ratios, that is x1 by x0 equals to j1 by m into j1 by m by 2 into j1 minus m plus 1 to the power half, and x minus 1 by x0 equals to j1 minus m by 2 into j1 plus m plus 1 whole to the power half. Now applying the orthogonality conditions, that is equation 21.5, which translated for the present case looks as x1 square plus x0 square plus x minus 1 square equals to 1. By substituting in this equation the values of form equation 21.16, we have 1 by x0 square equals to 1 plus j1 plus m by 2 into j1 minus m plus 1 plus j1 minus m by 2 into j1 plus m plus 1, which gives x0 square equals to j1 minus m plus 1 into j1 plus m plus 1 by j1 plus 1 into 2j1 plus 1. We can determine all the x mu's as far as the magnitude and relative phase is concerned. Since this equation together with the above ratios determines only the square of one of the coefficients, the overall phase still remains to be determined. Here we recall that in the preceding module we adopted the convention that scalar product of two vectors j1 j2 into j1 j2 with j1 plus j2 into j1 plus j2 is equals to 1. This choice means that positive square root is to be taken because x1 equals to 1 for m1 for m equal to j1 plus 1. Thus we write the first three elements of CG coefficients as x1 equals to j1 m minus 1 1 scalar product with j1 plus 1 and m equals to j1 plus m into j1 plus m plus 1 by 2 j1 plus 1 into 2 j1 plus 2 to the power half. x0 equals to j1 m 0 with a scalar product with a vector j1 plus 1 comma m, which is equals to j1 minus m plus 1 into j1 plus m plus 1 by 2j1 plus 1 into j1 plus 1 to the power whole to the power half, and x minus 1 equals to j1 1 comma m plus 1 comma minus 1 in the scalar product with a ket vector j1 plus 1 comma m, which is equal to j1 minus m into j1 minus m plus 1 by 2j1 plus 1 into 2j1 plus 2 whole to the power half. Now before writing the expressions for these CG coefficients which are given in the tabular form below, we should mention that similar procedure is to be adopted to evaluate the CG coefficients for the cases j equals to j1 for mu equal to minus 1 and 0 and j equals to j1 minus 1 for mu equals to plus minus 1 and 0. Setting the phase convention of the C coefficients, the important point to note here is that in the coupling of angular momentum j1 with j2 is equal to 1, the total angular momentum j can have the values j1 plus 1, j1 and j1 minus 1. And for each value of j, mu has the values plus 1, 0, minus 1. Thus, as a result, in this example, we have to write the 9 elements in the form of a matrix as given in the next slide. You will notice that in obtaining the second and third rows, ambiguity in the overall sign of each row is once more found. The rule applied for the first row above does not apply here. Note that these questions of phase convention are a general characteristic of unitary transformation. A change in overall phase of any row or column of a J1 1m minus mu comma mu, the scalar product with a kth vector j. The values of j for mu equals to 1, mu equals to 0 and mu equals to minus 1. For j1 plus 1, for mu equals to plus 1, j1 plus m into j1 plus m plus 1 by 2j1 plus 1 into 2j1 plus 2 whole to the power half. For mu equals to 0, j1 minus m plus 1 into j1 plus m plus 1 by 2j1 plus 1 into j1 plus 1 to the power half. And for mu equal to minus 1, j1 minus m into j1 minus m plus 1 by 2j1 plus 1 into 2j1 plus 2 whole to the power half. For j1, for 3 values of mu for mu equals to 1, j1 plus 1 m, j1 minus m plus 1 by 2j1 into j1 plus 1 whole to the power half. For mu equals to 0, m square by j1 into j1 plus 1 to the power half. And for mu minus 1, j1 minus m into j1 plus m plus 1 by 2j1 into j1 plus 1 whole to the power half. For j equals to j1 minus 1, for mu equals to 1, it is j1 minus m into j1 minus m plus 1 by 2j1 into 2j1 plus 1 whole to the power half. For mu equals to 0, it is j1 minus m into j1 plus m by j1 into 2j1 plus 1 whole to the power half. For mu equals to minus 1, j1 plus m plus 1 into j1 plus m by 2j1 into 2j1 plus 1 whole to the power half. Unitary matrix, that is multiplying by a common factor exponential I delta, where delta is real, does not alter the unitary character. This can be readily seen by inspection of the orthogonality relations equation 29.5 and 29.9. We here adopt the convention in an ad hoc manner by specifying that C coefficients for m2 equal to minus j2 shall be non-negative. This explains why in the third row the first element is to be taken as positive, and as a result the second has a negative sign. You can easily ensure by writing the sum of the square of the elements in each row that the orthonormality relation given by equation 21.5 is built in. Evaluating CG coefficients for the case of J2 equals to half. Let us apply the above recurrence relation to a simpler case of J2 equals to half. Here, since m2 is equal to plus minus half, we have to calculate the values of 4 CG coefficients only. To calculate the CG coefficients for the first row, that is for j equals to j1 plus half, here too we introduce the symbol j1 half colon m minus mu comma mu with product with the j1 plus 1, j1 plus half comma m kth vector equal to x mu, where mu equal to plus minus 1 by 2. Thus, for the case j equals to j1 plus half and m equals to m1 plus half, using the recurrence relation equation 21.13, j1 minus m plus half into x half equals to j1 plus m plus half into j1 minus m plus half to the power 1 by 2 into x to the power minus 1 by 2, or x to the power 1 by 2 equals to j1 plus m plus half j1 by j1 minus f plus half whole to the power half into x equal to minus half. Again, using the orthogonality relation, that is modulus of x half square plus modulus of x minus half square equal to 1, we get 1 by modulus of x minus half square equal to 2j plus 1 by j1 minus m plus half. Choosing the proper sign convention, we get x half equal to j1 half colon m1 m minus 1 m minus half comma half with a scalar product with a vector of j1 plus half comma m, which is equal to j1 plus m plus half by 2j1 plus 1 to the power whole to the power half, and x minus half, which is equal to scalar product of the vectors j1 half semicolon m plus half comma minus half with j1 plus half comma m, that is equal to j1 minus m plus half by 2j1 plus 1 whole to the power half. This gives x 1 by 2 by x minus 1 by 2, which is equal to minus of j1 minus m plus half by j1 plus m plus half whole to the power half. Using the orthogonality relation, that is x 1 by 2 square plus x minus 1 by 2 square equal to 1. Using equation 21.24 in 21.25, we get x half equals to j1 half and m1 m minus half and half product with j minus half and m, that is equal to minus of j1 minus m plus half by 2j1 plus 1 whole to the power half, and x minus half equals to vector scalar product of j1 half m plus 1 m plus half and minus half with the vector j1 minus half m, which is equal to j1 plus m plus half by 2j1 plus 1 whole to the power half. Note that in conformity with the sign convention used, we have measured the CG coefficient must have a positive sign for m2 equal to minus j2. That is why the third element in the 2 by 2 matrix corresponding to m2 equal to j2 equal to half is provided with a negative sign. The table for this matrix is given below. Product of j1 half m minus mu comma mu into jm. For j equals to j1 plus half and for mu equals to half, it is j1 plus m plus half by 2j1 plus 1 whole to the power half, and for mu equals to minus half, it is j1 minus m plus half by 2j1 plus 1 to the power half, and for j1 minus half, it is for mu equals to half, it is j1 minus m plus half by 2j1 plus 1 to the power half, and for mu equals to minus half, j1 plus m plus half by 2j1 plus 1 to the power half. Example 1. Addition of orbital angular momentum and spin of a system. To see how the values given in the table 21.1 are to be used, suppose we couple j1 equals to l equals to 2 with j2 equals to s equals to 1 to get the total value of j equals to 1 and m equals to 1. Since the value of j1 chosen is 2 and the required value of j is 1, clearly the elements in the last row would only be relevant. As for the value m equals to 1, this can be obtained when 1 mu equals to ms equals to 1 and m1 equals to ml equals to 0. Number 2, mu equals to 0, ml equals to 1, and number 3, mu equals to minus 1 and ml equals to 2. This is how, by substituting the values obtained above, all the 3 elements in the last row are to be evaluated. To get the physical picture, let us suppose that the eigenfunctions corresponding to are the spherical harmonics y, l, m, l, theta, phi, and the eigenstates for j2 is equal to s are the xs, ms, and the coupled state is represented by j, l, m. As the allowed values of all the quantum numbers are fixed, we can now write the coupled state in this representation as example of coupled state with j1 equals to l equals to 2 and j2 equals to s equals to 1. Now j11 equals to square root of 1 upon 10 y20 chi 111 or x11 or x11 minus square root of 3 by 10 y21 x10 plus square root of 3 by 5 y22 x1 minus 1. Note that the representation given above finds its use in writing the coupled spin angular momentum state for the deuteron, where the spin triplet state, that is s equals to 1, is coupled to l equals to 2 state corresponding to the non-central tensor force to write the deuteron state in j equals to 1 and m equals to 1. This procedure can be extended to find the expressions for any set of permissible values of j and m. So students, let us now summarize what we have learned in this module. To derive the orthonormal properties of the CG coefficients, we have learned how some useful symmetry relation between the CG coefficients. We have learned how with the help of the recurrence relation one can derive the expression for the LG coefficients, CG coefficients. Know to use the recurrence relation for a few cases.